acids and bases can be powerful substances that allow things to happen. And so in the lab, we know that we're very careful with them. And even outside, we see that they can be quite destructive. So here is a sculpture that was made probably of limestone of some sort, and it's actually been degraded by acid rain. And we see down here there's a forest that's been degraded from acid rain. We also know that we actually once upon a time had to evacuate Lewis and Clark High School because of an acid spill. So whether that actually has to do with strength or not might be the question, but we know that the strengths of acids and bases are things that we can learn about, and we know that the reason that we evacuated our building was because of a strong acid, hydrochloric acid. So we're going to take a look at those today. Grab your Cornell notes and let's get started. So the first thing is, what is a hydronium ion? And you'll see this in place of hydrogen ions, and really I use them very interchangeably, and so do many other probably chemistry teachers out there. So hydrogen ions dissociate in an acid, and they combine with water molecules to form a hydronium ion. And so the hydronium ion is the H3O+. And so you can use these interchangeably to talk about acids. We talk about hydrogen ion concentration, but really that hydrogen ion is forming with another water molecule to become hydronium. So you may see that both ways, and we'll talk about them interchangeably. So what makes an acid or a base strong versus weak is the question of the day. And a strong is something that is going to ionize or dissociate completely. So whether it's a strong acid or a strong base, they will dissociate or ionize completely. And so what we find is that with strong acids, they break apart into the hydrogen ions and an anion, and of course that hydrogen ion, cation, is going to form with water in order to make a hydronium ion. And so here's hydrochloric acid. When you put it in with water, it's going to dissociate into that hydronium ion and chloride ion. And so we see it breaks apart completely. And the same thing happens with a base. And so these are going to be ones that break apart into a cation and hydroxide as their anion. And so here's an example of KOH that is being added in with water, and it breaks apart into potassium ions and hydroxide ions. So they're completely breaking apart. Now, weak acids and weak bases, on the other hand, do not ionize or dissociate completely. And so what happens is they're going to form equilibrium between the acid and the base and the conjugates in the solution. And so we see a weak acid, such as acetic acid. You probably commonly think of this as vinegar. And so when this goes in, it's going to form an equilibrium, and that's where we're getting that double-sided arrow down here to show that we actually move back and forth between these. So we're going to form the ions, and then they're going to go back and form the acid form as well. And so, or the acetic acid. And so they'll go back and forth between them. And because they don't dissociate completely, that makes them into a weak acid. The same thing with a base, and probably our most common weak base is ammonia. And so ammonia actually dissociates, and it's going to end up being NH4+, and then it ends up in doing that in the way it combines with water, generating some hydroxide ions, and that's actually why it's a weak base, but it'll go back and forth between those. So we need to know about acid dissociation constant. So when we have these weak acids, and we can even look at strong acids with this as well, we want to know the relative strength of these acids. And so acid dissociation constant is Ka. So this is an equilibrium thing again. And it's the ratio of ionized and undissociated forms of an acid. And so we have this example right here. So here's our acetic acid again that's been added with water, and when it does that, it's going to break apart into those ions, and we're going to form the equilibrium. Oops. And so when we do that, we can write an expression for this, just like we have been writing expressions for other things. And so our Ka is going to be equal to the concentration of our ions. You could also put just an H+ here if you wanted to write it that way. And our anion here, C2H3O2 acetate, okay, divided by the concentration of the non-broken apart version of this. Okay. And so that's how we would write the expression for this. Weaker acids have smaller Ka values relative to stronger acids. So we can look at this on a relative scale to one another on how strong or weak they are to one another. And that's something that might be helpful from time to time. Okay, so we probably want to know how Ka is calculated, and that is really the one that I will have you calculate. So here's our question. What is the Ka of a 0.100 molar solution of acetic acid with a pH of 2.9? And we have our equation that's given to us, and so a lot of times I will give you these, and we want to know how to set this up. So the first thing that I want to do is I want to go ahead and reset up that Ka, that equilibrium or the acid dissociation expression. So that was our H3O plus hydronium and our acetate C2H3O2. I have the condensed format for that there. And then on the bottom we'll put our non-dissociated form. So that gives us just basically what we have to plug in, but we need to do something a little bit different for these ones. And so this is what we consider to be what we call an ICE table. And so it's the change in the equilibrium. And if you think about this, I think about the way that I write my equilibrium expression this way. So this is the two sides of the equation. And then we have the change, and what happens at equilibrium. And so I kind of draw a couple lines here. This helps me organize. And so in this, we see that we have a 1 molar solution of acetic acid that we start with. So I'm going to put the 0.100 molar. Now, before this dissociates, we have all of the concentration is actually in this format. And so here, we don't have anything. Now, once it dissociates, that's what we're going to look for is at equilibrium, what are we going to have for those values? And then we'll plug them in. Now, we have to be able to do something to get our hydronium or hydrogen ion concentration. And so to find that, what I have to do is I have to take, to find the concentration of H plus, remember, or H3O plus, okay, we're going to do 10 to the negative 2.9. So that comes from the last video that we watched. And that tells me when I plug that into the calculator, I get 1.3 times 10 to the negative third. Okay, so that's the concentration of hydrogen or hydronium ions interchangeably there. And so I know that we're going to add 1.3 times 10 to the negative third here, because when this thing breaks apart, that's how many ions I'm going to have. And I'm also going to add the same amount since we have equal parts that split apart in that dissociation. I'm going to have 1.3 times 10 to the negative third here. Now, the amount that I gained in my products of this, or on the ion side, has to be subtracted from the other side. So I'm going to subtract 1.3 times 10 to the negative third. Okay, so now what I do is I add up each column. And so when I take 0.1 minus 1.3 times 10 to the negative third, I get 0.099, okay? When I do that here, I started with 0, so these ones are just going to be, 1.3 times 10 to the negative third, and 1.3 times 10 to the negative third. So now I can actually plug those into my expression. So to find my Ka value, on the top I'm going to have 1.3 times 10 to the negative third times 1.3 times 10 to the negative third, and then I'm going to divide that by 0.099, excuse me. And when I calculate that all out, I end up with a Ka value that is 1.7 times 10 to the negative fifth. Okay, we might use that to compare to other things, or we just might want to know what the Ka value is. So again, we want to set that up in our ICE table, and then we will end up adding up and plugging those values in. And so we'll take a look at that again in class and try that in some practice problems. Okay. The last thing that I want to talk about is how are strengths and concentration different? And so we've talked about strengths, and we've been talking about concentrations of solutions for quite some time. So strength depends upon complete ionization or incomplete ionization, and so that's the strong versus the weak. We measure this, or we calculate it using pH. And for concentration, it depends on how many ions in a volume of solution that have dissolved, and it's measured or calculated in molarity. And so what I really want you just to remember is that strength is not equal to concentration. We can have a weak acid that has a very strong, high molarity, or we could have a very strong acid that has a very small molarity, but they're not the same thing. We might be able to use them both to be able to determine things though. So I hope that was helpful, and we'll take a look closer at these when we get back to class.